Right, good morning, folks. I hope we're all well. Yet again, another Wednesday webinar. This time around, we're going to be talking about hot air. Hot air is one of those things. Passive stack ventilation explained is the name of the talk. In fact, when I came to writing a presentation on passive stack ventilation, it was going to be reasonably short. As interesting as it is, there's not mega amounts of content. So we've padded it out and included other forms of ventilation as well. But it's a it's a look into various different types of ventilation, and we've got a case study in there for you, and we'll be touching on domestic and commercial applications for ventilation as well. We're recording this. It's going to go up on YouTube as normal, so you can watch it after if you have to leave early, or you know somebody else who wants to watch this and isn't able to make it. Normal kind of admin, do keep your mics on mute, and by all means do turn your video on. It's always good to see some faces. So without further ado, for those of you who are new to Mesh Energy, just a minute on what we do and what we're about. Essentially, we're independent energy consultants, and we're trying to keep things simple and often work with architects and design teams to help deliver more and more successful low energy buildings. We pride ourselves on quite an extensive toolkit that we have, as well as many decades of combined experience between us. And there's very little that we don't know about low energy buildings. So we're always interested to learn new things, and more than happy to share webinars like this, what we do know, to try and accelerate the process to decarbonising the UK and the built environment. We're based in Farnham, friendly bunch of people, and as always, we're reachable via the website or on email. So if you do have any questions after this, do let us know. We've also got the chat box as normal, which is open for questions. So if you put in your questions, we'll answer those at the very end as well. So as I say, and I would say just at the top here, just by way of a disclaimer, this is by no means a technology masterclass. This is a kind of a reasonably kind of high to mid-level review of ventilation. David Reed, our in-house masterclass expert, does a fantastic job at really going into the detail of these things. This is as I say, this is an easier and some may argue a more digestible way at reminding ourselves about ventilation techniques used in building design. And so do bear that in mind when we're going through the content. But the discussion areas that we will cover this morning are on ventilation types, an introduction to those, air effects that particularly drive different types of ventilation in the built environment, looking, as the title suggests, specifically at passive stack ventilation systems. If you have showed up just for passive stack ventilation, we haven't left that off, and that's a particular bit on those ventilation systems, and we'll talk about how it uses the effects that we've covered before that. We'll do a case study on a project that we've covered before in overheating analysis and various other presentations. We'll show you how that building was designed to maximize the use of natural ventilation. And then we'll kind of finish off with some commercial ventilation ideas of how you ventilate bigger, higher occupancy buildings. And then we'll summarize as usual and try and wrap it up. So without further ado, let's get going. So ventilation types, these are kind of really split into three main areas. The first is natural ventilation, and under the natural ventilation umbrella, there are three different types, and these are the effects that we're going to be going through on the next few slides. And this is using buoyancy, or the thermal stack effect, cross ventilation, or is otherwise known as the wind effect, and then wind or the Venturi effect. So those three different subtleties in using the natural properties of air allow us to ventilate buildings. And this, as I say, falls under the natural ventilation umbrella. So very low tech, and lowest cost, as you will see. Mechanical ventilation, again, there's more and more talk about this. You know, there's good old-fashioned mechanical ventilation and heat recovery that David we covered in a masterclass series before. But you've got exhaust-only systems, supply-only systems, and these rely on machines and forced ventilation to help us better ventilate our buildings, and they bring in heat recovery and various other things. And invariably, the cost goes up and the complexity as well. But for certain situations, you know, you need mechanical ventilation, but there is more involved there. And then you've got hybrid ventilation as well, which is a kind of a mix between both of those. And we've got spot ventilation, which is used. So we're not going to cover those last two. We're going to focus on natural ventilation and these effects next that we've specifically pulled out there. And I guess just starting at the top, it's always, we live in an ever complicated world, and it's always tempting to be smart, to be clever, to overcomplicate designs, to try and find the new and kind of quirkiest thing to put in a building. But actually, I've used the analogy of an iPhone before. Simplicity lies, or beautiful design often lies, particularly around sustainable buildings, in simplicity. And so if we ask ourselves the question, why natural ventilation? Why is natural ventilation important? Well, the actual purpose of providing natural ventilation in the building is to achieve maximum human comfort indoors by utilizing maximum natural energy and resources. So this is talking about using, you know, energy and resources that swirl around us and our buildings every single day to try and maximize or go as far as possible in making a comfortable place to live for ourselves before we start introducing technology and man-made things and using excess electricity, which has been generated by, you know, God knows, however, whatever means. So really focusing on how we can do that through better building design and using the natural laws of physics. And so it's worth just kind of thinking about this when you start any project, really, just to make sure you keep it as simple and effective as possible. So if we look at the first effect here, it's about buoyancy, and it's sometimes called the stack effect. And as you might have got from the title, it's about the thermal properties of air. And so it relies on the natural thermal forces of air and difference in air temperature. And when we get a difference in air temperature, we get this kind of natural movement of air from high to low pressure areas. So invariably, low temperature areas are high pressure, and high temperature areas are low pressure. And so, you know, we physically see this in buildings, and this is why we open, you know, high level windows, because we know that warm air rises, and you can exhaust. This is exactly why we've got chimneys that are high, because hot air rises and can exhaust at high levels of a building. And it's just the temperature differential that causes warm air to rise. But also I guess in a closed environment, as warm air is expelled from a building or an outlet, it actually replaces the air that was in the building with cooler air. So you end up with this kind of natural cycle of cool air being brought in, hot air being exhausted out. And of course, during summer, that has a massive effect on cooling, and also doubling up with greatly improved ventilation as well. So a quick kind of whistle stop tour there, but when people talk about buoyancy and the stack effect, this is fundamentally what we're talking about. And this little diagram shows exactly what we're talking about here. So you've got openings at the top of a building. This is a kind of a chimney, but also you've got a high level opening in this building, and air is being brought in through doors and windows and naturally rising and venting through these two high level openings in the building. And because temperature drives this effect, you can actually supercharge it through design and color, funnily enough. And so what you tend to find on more innovative buildings is the use of high level windows or high level solar collectors, which make the top of the building, I mean, roofs are really good for this, particularly black colored roofs or dark colored roofs. What you end up with is when you paint things different colors, or when you allow more solar in at the high level of a building, it heats the air in the top of the building. And as I say, it supercharges, you end up with a higher pressure differential and you can end up with more effective ventilation. It does require some proper design, but there are some pretty basic tools that are used around the globe, not just in the UK, to drive this buoyancy stack effect and really keep technology to a minimum, just using temperature differential and physical properties. And again, here are some typical sections, and this is just kind of a sketch that I got off the web of different building designs here. So you can see from the simple to the bit more complex, deeper building designs. You've got central atriums where you can draw air in and vent at high level. You know, maybe in a domestic vaulted ceiling application, again, you draw in air at low level and you exhaust that air at higher level, and then you've kind of got bits in between as well, staircases, using staircases as your chimney. There's all kinds of different design iterations, and no doubt you guys will have seen this. And these principles are simple. There's nothing complicated about them. It just shows you some of the ideas that you can explore if you're particularly interested in using stack ventilation or the buoyancy effect in your next design. The other one, again, which hopefully we are all familiar with, is cross ventilation. And this is sometimes known as the wind effect and relies on wind. It relies on air movement to create positive and negative pressure on buildings, to move air from one side of the building through the building to another. And you've got doors, windows, grills and stuff that you can let air in through. And then on the other side of the building or another aspect of the building, you've got outlets, again, doors, windows, grills that you can open to vent out that stale air. So again, we're improving kind of ventilation and improving thermal comfort and keeping the temperatures down, particularly during summer months, and ventilating during the winter months. And invariably, if you look at a building in section where you have wind blowing on a building, that's creating a positive pressure. And on the leeward side, you've got a negative pressure. And again, the laws of physics mean that the air will move from that positive pressure area to that negative pressure area. And again, that the air movement will naturally happen through the building. And again, a bit like this diagram shows, you can have that happen across the entire width of a building, or you can have it kind of short circuiting between aspects of a particular room. But having these routes through a building allow the most optimum ventilation and really allow you to minimize the areas of stale air in the building and keep ventilation at its very highest. The only slight issue is on still days, you're going to have an issue here. So we've all been, you know, in buildings where it's hot and muggy and there's no wind and it's an absolute killer. That's where, you know, a blend of these things in building design really comes into its own, because thermal or using the stack effect or the buoyancy effect works absolutely fine on non-windy days, because you've got warm air rising and you don't need wind for that to work. So have a think about mixing some of these things in building design to really cater for year-round performance. And the third and final effect that I want to talk to you guys about is about the wind and Venturi, or sometimes called the Venturi effect. And this uses, again, air movement and Bernoulli's principle to help move air from a building just through using the velocity of air. And again, it relies on air movement. And for those of you who don't want to dive into your physics books or don't remember what Bernoulli's principle is, this says that an increase in airspeed means a drop in pressure. And we can use this in building design to our advantage to help us move air. And so, and this picture is quite an interesting one. This is a Z-beds, quite a famous Z-beds photo. And these devices, albeit they look quite quirky on the top of these buildings, use the wind and Venturi effect to ventilate these buildings. As you can see, there's a lot of solar panels and very eco-friendly, low-energy buildings. But if I use this photo to describe what we're talking about here, so these weather vanes on the top of these devices are you know, doing exactly that. When the wind is blowing, it points this smaller spigot into the wind, and so the wind is rammed into the smaller spigot here and driven into the building. And so essentially the air is scooped up, fresh air is scooped up. And on the leeward side, as wind passes past that, you have a low pressure area which is created, and that draws air from the building out and expels air up the other side, and as I say, out of the building. So again, you get this natural kind of cycle of fresh air in, and just through using the Venturi effect, you can suck stale, warmer air out of the building as well. So very, very simple. This is just one solution. You can use more primitive versions than this, but I say this was obviously a big design feature for these buildings. But this is, this is another effect that you can use in your arsenal, in your design to, again, use the natural effects of wind to help you out ventilate buildings without including technology in there. And so having covered those effects, well, let's come on to what we kind of titled the talk about, which was passive stack ventilation. And in fact, passive stack ventilation is kind of combines all of these really in different ways. And invariably all of these different effects kind of come into a building's design, whether you like it or not, because we've always got changing temperatures and moving air and various things. So, passive stack ventilation is a culmination of that, and is a very well-known industry title. And it's often used in most cases to ventilate places where you've got stale, dirty, smelly air, stuff like WCs, kitchens, utility rooms, and bathrooms. That's typically what it's used for, but it can be used to ventilate other rooms as well. And again, to keep things simple, you often use vertical ducts with minimal bends. This example that I took off the web is a pretty standard example. You capture the air using the Venturi effect across the top, as well as a bit of stack effect. And it's just a straight run. The air rises and is vented out and is brought in through trickle vents and window openings and doors and things at lower level, but finds its way up and out of the building. Duct sizes, though, a bit like mechanical ventilation and heat recovery, really. We're not talking about moving air at high velocities here. So the cross-sectional area of the ducts is quite important, and they have to be reasonably large. 80 to 125 millimeters is a typical section for these, to make sure we can get the right air changes and ventilation rates. And that can cause some issues, and certainly should be designed for at the early stages of a building, to make sure that you've got appropriate risers and what have you to really make this particular type of ventilation as effective as possible. So advantages, and these advantages here run out to some of the other effects, and actually are advantages of natural ventilation as a kind of an umbrella term anyway. As we drive for more energy efficient buildings, it's worth remembering that natural ventilation, as I say, it's been used for hundreds, if not thousands of years across the globe, is the most energy efficient way of ventilating a building. There is nothing more efficient than using the natural energy that we've got around us and the laws of physics, and we can steer clear of machines to help us out in its purest form. And so there's zero or almost zero capital expense to put these systems in, which should last the life of the building, all being well. And it's the cheapest form of ventilation when you look at lifetime cost of the building. One of the other advantages, it reduces humidity and ventilates all the time. Now that can be a disadvantage as well as an advantage, but it ventilates all the time. It naturally happens in the background, and there's little or no maintenance required. And unlike a mechanical ventilation heat recovery system where you have a working fan there, which can create noise and you're forcing air movement, these systems, because they are dealing with natural pressure differentials, are totally silent. You're not forcing, you're not forcing air. Again, this can be a positive or a negative, but if noise is a concern, these systems are dead silent. One of the other advantages, particularly in summer, is that they can be used to cool at night. So, you know, with overheating becoming more prevalent, and we've done a CPD or a webinar on this, you know, how you purge hot air out of a building is really, really important during nighttime to maximize occupant comfort during, you know, when the sun's gone down. And these systems can allow you to do that. The warm air rises, comes out the top of the building, you're bringing in cooler air, and just allows you to clear that that really uncomfortable hot air during the course of the night, so you get a better night's sleep and are refreshed for the morning. The disadvantages, though, and there are disadvantages with all these things, are that it can create drafts. You know, when you talk about air tightness of the building, you know, you wouldn't necessarily put these in a very airtight building per se. And that conflicts with some of the trends that are currently happening to make more airtight buildings. So you can create drafts, which may be suboptimal for building comfort. Large ducts, so you need to factor in risers and surface areas for these larger ductwork. It is difficult to retrofit for existing buildings. That can create an issue. And it's difficult to control air movement as well. You know, you can't have your cake and eat it in most cases. So if you're allowing nature and the laws of physics to do their thing, you know, controlling air movement every single day of the year can be very, very difficult. And so you need very, very careful design just to make sure it's working, you know, for the vast majority of the year. And there's no opportunity to filter air either. As you add in more filters, you're creating natural resistance to the airflow. So I say it's not all advantages, it's not all roses. There are some disadvantages with this stuff, and like all good designers, you know, we've got to balance where this is appropriate and where it's not. But hopefully that gives you a kind of a rounded idea. And this gives you an idea of the types of products. They make a statement, particularly in most of these photos that I've listed here. You know, some typical manufacturers, again, we're not sponsored by any of these manufacturers, but a quick Google search, and in our experience, these are the guys who are creating some of these products that you can see in some of these photos. And again, you've got, you know, some pretty futuristic looking things, but at the end of the day, these are just vents. You know, they're just vents in the top of the buildings. And in that bottom right-hand one, particularly colorful vents. So you've got companies like Monodraft, Ventive, Tech, and Passive Vent and stuff that produce these. And I can see a question that we've got from Zach. We'll come back to some of these. And there are some kind of hybrid products that you can get as well. So invariably, these manufacturers will do a whole raft of products from very, very basic to very, very complicated to help you with your particular ventilation strategy. And so that's the kind of the bare bones theory. Let's just have a quick look at a case study and some commercial applications, and then we'll kind of wrap up. Now, this is an interesting case study for a number of reasons. And say, if you've been on a number of our webinars, you'll recognize this one. But as the title suggests, this was actually in natural ventilation, a real success story. And actually, it does go to show how simple you can keep building design even in the 21st century and maintain thermal comfort both in the summer and the winter. So this is a project called Cole's House, a kind of a shout out to AR Design who did this design. We worked on this project probably about 4 years ago. It was completed a couple of years ago, just before a very, very hot summer that we had a couple of years ago. Yeah, pretty sizable domestic property. Located in the middle of nowhere. It certainly wasn't an urban environment, and a lot of trees around, a lot of woodland. High thermal mass building, a lot of in situ concrete was used. So as I said before, not necessarily an eco building, but we're talking about ventilation. As you can see, a lot of glazing was used on the eastern elevation where a lot of the living space was. So on the other side of this pane of glass here, we've got the main living spaces, we've got the master bedroom, and this is where the couple, although they had children, they were at university, this is where the couple spent most of their time, the other side of this 80 square meters of glass that they had on this elevation of the building. And the architects, particularly here, did have natural ventilation at the core of their design. And as you can see here, and we'll talk a bit more about this, you can see we've got this kind of tower structure. And although this was a CGI, it was built slightly differently. It actually went up higher, had a square top, and actually had a study at the very top. But you can see here, the roof slopes up, and there were multiple penetrations, doorways into an in situ cast open concrete staircase that ran up this, what essentially was a chimney, but the staircase led up to a study. And then they had a kind of a 360-degree panoramic view at the top of this building. So you had sloping ceilings, a lot of openable windows, and passive stack ventilation was, you know, where the architects were heading with this design. And they made a conscious decision here not to put in mechanical ventilation or cooling. You know, they hung their hat on high thermal mass, good air movement, and the building design really lending itself to, as I say, having this chimney and a path for the air to find its way to that chimney and then to escape at high level. What isn't obvious from that previous CGI as well is that there was a central courtyard. So this is, I you know, rarely I got my pen and pencils out. I had my architect head on the other day. I got my pen and pencils out and just pulled out the main walls of this development to kind of show you in its form. So quite a, you know, reasonably complicated, lots of angles and bits and pieces in this. But I want to pull out a couple of key features on this building. So this was the tower that you could see. So the CGI is a view from here, and this is the eastern elevation with all the glass that you could see. So we've got this main tower, which runs right up, you know, kind of 2-3 stories right up. But also there's a central courtyard in this development as well. So a pretty angular donut, but there's a central courtyard and there's a tower. And the courtyard features, has a really interesting application as well, because there's a number of things happening here with the ventilation. If we focus on the tower, we have the sloping ceilings which lead the hot air to that tower. The hot air rises and escapes at high level. But the courtyard is, again, critical to the success of this project, because what it allows for is cross ventilation. If you just had that tower, it would be, although you would get a bit of cross ventilation in these individual rooms, there would be quite a tortuous path for air to get right round the building all the way to the tower to eventually escape. And you may have found that there was overheating issues in part. I'm not saying it would fail as a building, but you may have had warmer temperatures in other parts of the building. But with cross ventilation, particularly during the summer, this allows loads and loads of different paths into the courtyard, out of the courtyard to the tower, and really allows maximum ventilation for what is a reasonably complex kind of floor layout for the building. So as I say, it's invariably, there's a number of these effects which are combining to create effective ventilation. And you've got a mix of this stack effect in the tower and cross ventilation working together here for this particular project. And this is a section, again, that I sketched up. This is obviously not going through the courtyard and draws in stuff through the windows and doors on both floors. And as I say, you can see this sloping ceiling that they've got, and you've got access into the tower from various levels. And then you've got this outlet at the very top. So I've just put some quick notes against this one, again, just to kind of help you here. And they had, you know, as well as opening windows and doors, they had trickle vents in this project. You know, I think the air tightness test that they did when they tested the building at the very end was, you know, around kind of 5 or 6 or something by way of an infiltration rate. Design is about 5 for building regs at the moment. So they had trickle vents all over the building. There's a lot of big glazing. You've got these sloping roofs, which are helping the air naturally move towards the tower. And then they also had, and this was critical to the building, and this did require a bit of technology, albeit a sensor and an actuator. The actual skylight opened, so it had a rain sensor on it, but also it opened when the temperature in that tower exceeded kind of about 26 degrees. So it would open and close and let warm air out. Obviously in the winter, when there wasn't a lot of warm air in the building, then that would remain closed and keep the warmth in, but it would open and close through the seasons to help, particularly during the summer. And alongside the heavy thermal mass of this building, it really worked wonders, as we'll see. So we modeled this building in our software as well. Funnily enough, it was actually modeled after the building was built. So they went about this in a kind of a backwards way. But this just kind of goes to show you analytically how this works. And this result here is for assuming these opening windows and the roof lights working and cross ventilation, and shows a particularly cool building, actually. So the maximum temperature that this dwelling reached in summer was a paltry 26 degrees, even with all that glazing. And again, I think this is a combination of the heavy thermal mass, but also the great ventilation strategy for this building. So in fact, we modeled this as a peak temperature of 26. And anecdotally, when I spoke to the client and he didn't know that we had run this simulation, he said the building got to a very similar peak temperature, even when it was 30 degrees outside. So a big success from the client's point of view, as well as the design team's point of view. The alternative is if you didn't have a proper think about ventilation here, and I've used this example before, is if you get confused here with what a mechanical ventilation heat recovery system can do for you and assume that that's going to solve all your problems, and you don't have opening windows and you don't necessarily think about ventilation appropriately, this is the alternative. So we actually modeled it using mechanical ventilation, no air conditioning in the building, not having a kind of a sensible window opening schedule and cross ventilation. As you can see, colors, picture tells a thousand words, and very, very, very different story here. And the peak temperature in this building was in excess of 35, 36 degrees. Now this, would cause health issues and would be highly uncomfortable. So you can see here, there's this kind of 10-degree difference for this particular building that was made out of heavyweight concrete. Just goes to show the difference in ventilation strategy and what that would practically cause to the occupant, were it not to be carefully thought about. And I know we've got some guys who deal with more commercial buildings, and again, there's probably a whole nother discussion on commercial buildings. But what I thought it was worth doing is showing you for more higher density buildings and larger volumes, how this can be used outside of the domestic realm. And again, very, very simple principles, but I've just got a few pictures here which we can talk around. So the first here uses a very, very kind of open space that you might see in maybe in a community hall or a big lecture theatre or a big entertainment space, or Excel or something like that, and it has a massive kind of vaulted ceiling and airspace here. And this this particular example again is using the stack effect or buoyancy to help expel air at a high level. And in this particular example, you've got monitors. You can open and close the vents depending on the time of day and temperatures and what have you. And pretty simple, you're letting in air through openable windows and vents at a low level. The air temperature is building up. You're keeping the occupants who are at a low level of that particular building or room design comfortable, and the hot air is well away from the occupants and being vented as appropriate. Pretty basic open building design. The other one, if you use the example for, say, I don't know, an office or a block of flats that had separate offices and a central atrium, again, you've got to have a think about this differently, because if you're not careful, the individual office spaces or room spaces get very, very, very hot, and particularly those up top can really start to cook. It's usually okay for low-level occupancies, but as you get into these high-rise buildings with many floors, it can get pretty hot pretty quickly. And usually as well, these staircases obviously have a lot of windows in, or they're highly glazed, and so can exacerbate issues. So as this diagram suggests, again, you're pulling in air from low level. You're using these central atriums as kind of chimneys, and also in the individual flats, you have ventilation and a path for the air to, particularly in the summer, to be able to vent at high level. You've got cross ventilation through the individual rooms or the individual spaces. But also, this is really interesting as well. As you've got skylights at the top, they can ventilate. But remember what I said about using solar gain to your advantage. As you let more sunlight in at the top of the building here, you increase your thermal differential in the building, and you increase and accelerate the movement of air using that buoyancy and stack effect. So you encourage hot air to get out of the building at high level. And so this particular example uses, again, a few of those different effects where you have those self-contained little areas, but also have central atriums. And again, this one's actually pretty similar to the Coles example, but again, could be offices. It's kind of offices in this particular example. But you've got here, again, ventilation, cross ventilation in from the side. This particular example actually pulls in, so you've got service voids in the floors here, and pulls in kind of cool air trickling through, gets into the rooms through floor vents, and allows hot air to escape a high level in the individual rooms and at the very top through a big roof light here. But also, again, you've got this kind of chimney feature on the edge of the building, which allows that hot air to rise. But also at higher level, you've got wind that can whip across here and extract that air using the Venturi effect as well. So, there's nothing massively new here. You're just using different features to use these physical properties. And, although we've talked about overheating, you've got to make sure that the building performs in winter as well as summer. So summer overheating, great, you can use these effects, but you do have to think about ventilation as well during the winter when you're trying to keep warmth in, but you're trying to make sure that you're ventilating the spaces enough. So you might need a slightly different strategy, or maybe a hybrid strategy, or slightly mechanically assisted strategy for some buildings that you're working on as they get more complicated and there's more needs from the occupants through the seasons. So again, a really quick whistle-stop tour through commercial and domestic and some of the main effects. And just by way of kind of summarizing what we've gone through here, I can see some questions, so we'll leave some time for questions at the end. But these are the key things to kind of take away. So remember that natural ventilation is low energy. It's one of the lowest energy ways of ventilating a building. Temperature, pressure, and air velocity can be used differently or in combination to ventilate spaces. You can use height in the design, orientation, and openings to optimize cooling in the summer and improve air quality. But you must understand the strengths and the weaknesses of different ventilation options. Just because natural ventilation may be right in one particular circumstance doesn't mean it's right for everyone. So you must have a look at that on a case-by-case basis. And you must also be sure to balance simplicity with functionality. Just because something's simple doesn't mean it's right. And just because something is complicated doesn't mean it's right either. You've got to have a look at this in context. And also, and I encourage this more and more, but you must use your gut, come up with an early stage concept, and then quickly find out if that's going to practically work. You've got to use computational tools to your advantage in the early stages before you start going down a particular route that may not be optimal. So you must analyze the designs beyond, pen and paper at an early stage to really make sure that you can keep the design simple and fully functional. So folks, that is it. As I say, a quick kind of whistle stop tour through ventilation. Thanks for your time there. I'll look at some quick questions here and see if I can answer these. So Zach has asked about, are there any passive based MVHR systems? Yes, Zach, there are. I know Ventiv particularly are particularly good at that. Again, as I say, most of these companies do a kind of a bog standard natural ventilation systems, but they do these kind of hybrid systems that include for mechanical ventilation and heat recovery. Again, you've really got to speak to these specialists about how they work, but you can get essentially hybrid kind of mechanical ventilation heat recovery systems that work passively rather than being a dedicated MVHR system that's got ducts to every single room. So yes, that does work. Joseph's asked, can natural ventilation work successfully alongside an MVHR unit, or do the two compete? How might they coexist in a domestic setting where invariably patio doors and the like will open on warm days where air tightness is a priority? Does it become more about expelling excess heat via roof vents to avoid overheating? Yes, in a word, Joseph, you can do that. And again, you know, as great as natural ventilation in its own right is, you know, you can't get away from the fact that air tightness in buildings is becoming important. And I'm a big advocate for hybrid systems, particularly seasonally, because I think you can keep these things really, really simple in summer, and the thermal effects of air during summer and wind effects during summer can have a big effect on cooling properties during the summer. And you don't need mechanical methods to do that. But in winter, when the building's locked down, you do want to recover heat. Air tightness is important to keep running costs down, to make sure you're using as little heating fuel or electricity, which is fueling heat pumps and things like that, is kept to a minimum. I strongly believe you must use mechanical ventilation heat recovery, particularly in newer buildings. So yes, they can coexist. I think using them seasonally is a really interesting discussion. And you know, there are some people that switch off parts of their MVHR system and use in the summer so they can fling open patio doors and use skylights and stuff to greater effect without running up their electricity bills. So absolutely they can coexist. And as I say, I personally advocate looking at that more seriously to get that blend right between mechanical energy efficiency during the winter and simplicity and effective cooling without using air conditioning during the summer. So Roxandra is asking, this is mentioning about the Hampshire case study. Did you assess the heating load by any chance? It looks like it has a lot of external envelope, and although brilliant for ventilation, I'm wondering how it's performing in winter. Funnily enough, actually, Roxandra, the performance of the building was pretty good. As I say, it had a high thermal mass. It was actually pretty well insulated. I mean, the U values for the walls were kind of a bit better than building regulations, so around the kind of 0.17, 0.18 mark for the walls, you know, 0.13 for the roof. So nothing amazing there, but because it had a lot of thermal mass in the winter, it's actually particularly effective. It had underfloor heating throughout, and actually the thermal load was pretty reasonable. Yes, completely agreed. It did have a big surface to floor area ratio, and the glazing was very high spec. So it could have been better, but given its form, actually, it did pretty well. Sarah Swathi, sorry, apologies if I've got that name wrong. He's asking if we could just go through the last few slides. More than happy to do that. The last slides here we've got, I'm assuming you're meaning these slides that I didn't cover. This is just what we do as a business. So Mesh Energy can help at the various REBA stages here, from very early fag packet calculations through concept design, develop design, detailed design, and into construction, and onto stage 7 and handover. So we can get involved in anywhere you would like us to in the project for M&E package design. We really try and work with design teams to make sure we can offer an end-to-end service or a bespoke service if you don't need our full assistance through the project. And the final one here was just a question slide and a pretty typical kind of technology heavy home to show you some of the technologies that we discuss. So hopefully that's what you meant about the last few slides. Thanks, folks. Any last questions? Just whilst you think about any last questions, I'll run you through next week's webinar. Really excited about this one. We've got three webinars for the rest of the year before we wrap up on the 16th of December. The next one is by Gary Wilburn. So we've got a guest architect. These are proving really, really popular, getting architects involved in sustainability on once a month. We've got a growing list. We've got architects who've agreed to join on webinars from March or April, and we've got architects booked until March or April of next year. So next one up next week is Gary Wilburn from HPW Architects. He is the ACB, which is the Association of Environmental Conscious Building chair, but he's been part of HPW Architects, who are based on the South Coast for the last 30 years. And they do a lot of big sustainable projects. They've broken a lot of ground on big projects using water, and I think he's going to be talking about a lot of the water projects they've been involved in. Really exciting. So if you're into commercial projects and would like to see something that's beyond domestic, Gary's your man. Do book up in for that one. After that, we've got David Reed doing a masterclass the week after. And then a week after that, we're doing Zero to Hero again, looking at how your architect practice can become more sustainable. In the first week in January, we're going to be talking about Goldsmith Street, and Zach, again, who's on the call, will be talking at that one. Really excited about that. So we've got we're building the webinars that we've got coming up, a really exciting list. There is, oh, David's just responded there. Somebody's asked about passive evaporative cooling. That's booked in for the new year as well. We're trying to think of loads of new exciting topics. And I would invite you guys, you know, this is so important that you share with us what you would like to hear about. We can dream up all kinds of topics, but you guys make us keep giving these. And I can guarantee if you're thinking about a topic, there are 10, 15 other people that are thinking about that topic as well. So do share that with us, do email, do leave in the comments, and do share with us, you know, what those topics will be. And I will promise you that we will try and wrap those in as soon as we can do. So thanks, guys. I don't think we've got any other big questions for this week around. Thanks for your time. Hopefully you've learned something there. Rhiannon will get this presentation out to you further on today, and you can watch this presentation later on today on YouTube. I've seen just a final question come in from, I'm guessing that's Mr. Snelling, might be a Mrs. Snelling, C. Snelling. Where can you sign up for these, as they're not on your website presently? The new webinars are going to go up there. We're going to be putting them up very, very shortly, so do bear with us. If you join up to our mailing list as well, which you can get on via the website, you'll be sent a reminder. We'll bombard you. Link in with me on LinkedIn, and we'll put the reminders up there as well to get you guys signed up to those. So thanks, folks. Hopefully you found that insightful, and we will see you next week with Gary Wilburn at the helm. Thanks very much. Cheers. Take care. Bye. Bye.